Welcome back to the channel. Today we are diving into one of the most provocative debates in the philosophy of mind and cognitive science. In an era of large language models that seem to converse fluently, an old question returns with new urgency. Can a machine literally think? To answer this, we must revisit a paper published in 1980 by philosopher John Searle, titled Minds, Brains and Programs. In it, Searle draws a sharp line between two approaches to artificial intelligence. First, there is what he calls weak AI. This is the reasonable view that the computer is a very powerful tool in the study of the mind, allowing us to test hypotheses rigorously. But then there is strong AI. This is the bold claim that the appropriately programmed computer really is a mind, that by virtue of executing the right program, a machine can literally be said to understand and have genuine cognitive states. To challenge the claims of strong AI, Searle devised a famous thought experiment. Imagine you are locked in a room. You are given batches of Chinese writing. But here is the catch. You know absolutely no Chinese. To you, these characters are just meaningless squiggles, distinct only by their shapes. However, you are also given a rulebook written in English, effectively a program. This rulebook instructs you on how to correlate one set of formal symbols with another. People outside the room slip in symbols they call questions. You follow the formal instructions and slip back symbols they call answers. Suppose you get so good at following the instructions for manipulating these formal symbols that your answers become absolutely indistinguishable from those of a native Chinese speaker. From the outside, it looks like understanding. But inside the room, do you literally understand Chinese? Searle's answer is obviously not. You are merely instantiating a computer program performing computational operations on formally specified elements without knowing what they mean. This brings us to the core of the problem. Computer programs have syntax, but they possess no semantics. Let's enter the room. This thought experiment sent shockwaves through the cognitive science community. Proponents of strong AI fired back with a series of counter-arguments. Let's look at the three most significant ones and how Searle dismantles them. First, there is the system's reply. Critics argue, granted, the individual person locked in the room understands nothing, but he is merely part of a whole system. The entire system, the person, the rule book, the piles of paper, understands. Understanding is not ascribed to the individual, but to the system of which he is a part. Searle's response is simple and devastating. Let the individual internalize all of these elements. Imagine you memorize the rules in the ledger and the data banks of Chinese symbols, and you do all the calculations in your head. You incorporate the entire system. There isn't anything at all to the system that you do not encompass. Do you understand Chinese now? No. You are still just manipulating formal symbols, only now you are doing it in your imagination. And if you don't understand, then the system cannot understand either, because the system is just a part of you. Next, the robot reply. This view tacitly concedes that symbol manipulation alone is not enough. So it proposes, let's put a computer inside a robot. Let's give it a television camera to see, and arms and legs to act. Then the formal symbols will acquire meaning through causal relations with the outside world. Searle applies the same logic again. Suppose you are inside the robot's head. Instead of the computer, it is you receiving uninterpreted formal symbols from the robot's sensory receptors and sending out uninterpreted formal symbols to its motor mechanisms. You are the robot's homunculus, but you don't know what's going on. You manipulate symbols according to rules, but you don't see what comes into the robot's eyes, nor do you intend to move the robot's arm. In this case, the robot has no intentional states at all. It is simply moving about as a result of its electrical wiring and its program. Finally, the most fascinating one, the brain simulator reply. Suppose the program doesn't simulate language at the level of scripts, but simulates the actual sequence of neuron firings at the synapses of a native Chinese speaker's brain. If the machine simulates the formal structure of the human brain, surely we would have to say it understands? Searle replies that even getting this close to the operation of the brain is still not sufficient to produce understanding. To illustrate this, imagine that instead of a man shuffling symbols, we have a man operating an elaborate set of water pipes and valves. Each water connection corresponds to a synapse in the Chinese brain. When the man receives the symbols, he looks up in the program which valves to turn on and off. Where is the understanding in this system? The man certainly doesn't understand Chinese, and neither do the water pipes. The problem with the brain simulator is that it is simulating the wrong things about the brain. It simulates only the formal structure of the sequence of neuron firings, but it leaves out what matters: the causal properties of the brain, its ability to produce intentional states. Formal properties are not sufficient for causal properties. Simulation is not duplication. No one supposes that a computer simulation of a 5-alarm fire will burn the neighborhood down, or that a simulation of a rainstorm will leave us all drenched. Why on earth would anyone suppose that a computer simulation of understanding actually understood anything?